Hello everyone. In this lecture we shall discuss the finite differences. Basically the finite difference operators, their relationship and the properties of the difference operators. Suppose you are given a function y is equal to fx which are tabulated for equispaced values of the nodes. Means here xi is equal to x0 plus is. That means the gap between this is h, the gap between two consecutive nodes is h. So this is what it is called the equispaced. What is our objective? Our objective is to get the value of fx at a point A or value of this f dash x at the point A, where A is a point in between x0 to xn. Okay, and this is based on the finite difference calculus. Okay, so coming to the definition of finite difference calculus, the calculus of finite differences deals with the changes, as I have told you, the changes in fx. So the changes that takes place in the value of the function or the dependent variable due to the finite changes in the independent variable. So the change in x lead to a change in fx. This is to be estimated, and this calculus is known as the finite difference calculus. Okay, so here you are given y is equal to fx. X is called an argument here, and the dependent variable y for given x is called the entry or the functional value, and the gap between two consecutive node is h, is called the interval of differencing. Okay, so now we have some standard difference operators, forward operator, backward operator, and so on. Before that, let me to introduce myself. Myself, Professor Kumar Paikray, currently working as a professor in the Department of Mathematics at Veer Surendra University of Technology, Burla, Odisha, India. So let us now discuss the standard difference operators. Now coming to the forward difference operator, it is denoted by a delta here. Okay, if del is operated upon a function fx, then this node fxi becomes here fxi plus h, means next value minus this one fxi, or in short we write it next means fi plus 1 minus that same value fi, and this delta is also otherwise known as your descending difference. Okay, this delta is otherwise also called descending difference. Similarly, your backward operator is inverted del. Okay, if this del is operated upon fxi, means the same functional value minus the previous one fxi minus h, or in short we will write it it is fi minus fi minus 1, that functional value minus the previous one. And this inverted delta is also sometimes called the ascending difference. Okay, ascending difference. Similarly, coming to the shift operator, it is denoted by here capital E. So this, if E is operated upon a function fxi, okay, this functional, this now shifted to fxi plus h. That means this is same thing as fi plus 1. So now coming to the central difference operator. Now for example, if I ask del of f0, what does it mean? it means the next is f1 minus f0. If I ask, inverted del of f1 means the same f1 minus this previous f0. If central del f0 means it will incremented by half. It is suppose del f half, it is incremented half. So this is f of half, half plus half means f1 minus f of half minus half is your f0. Now these three things are same. We see here del f0 is same thing as inverted del f1 is same thing as here forward a central del f half. Okay. Similarly for higher order difference, similarly here del square f0 will be here del square inverted del square f2 will be your central del square f1, like that. In general, I can say del n fi is inverted del n fi plus n. Okay. So this is the connection between your forward and backward differences. Use some relationship among this operator. You see, it is easy to see that your del is equal to your e minus 1. Inverted del is equal to 1 minus e inverse. And your central del is equal to e to the power half minus e to the power minus half. And for your average mu is equal to half of e to the power half plus e to the power minus half. We can easily prove it one by one. You see the proof. We have del fxi is what? Fxi plus h minus fxi. Now this fxi plus h is nothing but efxi minus fxi. So this is e minus 1 fxi. So what we get? E minus 1 is del. Therefore del is equal to e minus 1. Accordingly, if I ask this relationship, okay, what is your del fxi? Del fxi is fxi minus fxi minus h. Okay, you see. So this is fxi and this will be your e to the power minus 1. When this is h plus h, then it is e to the power plus 1. It is minus 1 into h. So it is e to the power fxi minus e to the power minus 1 fxi. Okay, so this is equal to fxi taken common. It is 1 minus e inverse. So fxi cancelled in both the sides. Therefore what we are getting? We are getting inverted del is 1 minus e inverse. So from the simple definition it is very clear. So one may note here that e to the power or e square fxi. What does it mean? It is f of xi plus 2h. Okay. This coefficient here will be the power. E to the power n fxi will be fxi plus nh. E to the power minus n fxi will be here fxi minus nh. Okay. Next, coming to your central operator. If I ask del fxi, what does it mean? It is fxi plus h by 2 minus fxi minus h by 2. You see now, the coefficient of h is half. So this is e to the power half, okay, fxi. And this coefficient is minus half, e to the power minus half fxi. So you see, so e to the power half minus e to the power minus half fxi. So fxi cancel. So therefore your delta is equal to e to the power half minus e to the power minus half. And similarly here mu will be equal to half e to the power half plus e to the power minus half. These are clear cut from the definition itself. Now coming to some more relation. Now coming to another relations, suppose we want to prove one. Okay, as we have seen above, here del is equal to E minus 1, del is equal to 1 minus E inverse. On this basis we can prove that we have del is equal to E minus 1 and del is equal to 1 minus E inverse. Okay, so this implies, you may, if you like, you may prove it. This implies here 1 plus del, E is equal to here 1 plus del, and here E inverse, bringing this to this side, and this implies here E inverse is equal to 1 minus inverted del. If you multiply these two, so that means E into E inverse is 1 plus forward del into 1 minus backward del, and this is here 1, so this is equal to here 1. Proved. Coming to the proof of 2. So now coming to the proof of 2, we have del is equal to E minus 1 and inverted del is 1 minus E inverse. So this is 1 minus 1 by E. If you simplify, it is E minus 1 by E. So here this is del, so this means here inverted del by 1, cross multiplication. So this implies here E minus 1 is del E. You see, from this and this and this, here del is equal to inverted del E. Likewise here central del is E to the power half minus E to the power minus half. So multiply E to the power half and divide. So it is E minus 1 by E to the power half. Okay, so now you multiply it with this cross multiplication. So that means del E to the power half is E minus 1. So now you combine these three, this and this. So therefore del is equal to inverted del E is equal to E minus 1. So this is proved. So in that way you can adjust. Let us prove some more examples. So coming to the proof of this, here del square fxi is del fxi. So first you operate this. So this is del f xi plus h minus fxi. Okay, again you operate this del. So now operating this, it becomes f xi plus 2h minus f xi plus h, and operate this minus f xi plus h minus fxi. So if you simplify it, this is f xi plus 2h, this plus this minus twice f xi plus h minus minus plus fxi. This is nothing but e square fxi, is not it, minus 2e fxi, and this is plus fxi. So it is e square minus 2e plus 1 fxi. So this is here e minus 1 whole square fxi, is not it? If you continue in this way, here del square becomes e minus 1 square. If you continue in this way, here del to the power n will be e minus 1 to the power n, and similarly del to the power n will be 1 minus e inverse to the power n, and we can see it. Next, coming to another example. Now let us prove this. Coming to the proof, we know we have inverted del is 1 minus e inverse. Now coming to this right hand side here, now del into 1 minus del to the power minus half, substitute this value here. So is equal to 1 minus e inverse into 1 minus 1 minus e inverse, this to the power here half minus half. Now if you simplify it, 1 minus 1 and 1 cancelled. So this will give you 1 minus e inverse into e to the power half. If you multiply it, it is e to the power half minus e to the power minus half. If you recall, what is this? This is your delta, is not it? So therefore we get it, delta is equal to this into 1 minus this to the power minus half. This is now proved. Now coming to the second one, bringing this to this side. Okay, so here del is equal to del into 1 minus del to the power half. Okay, so let me to write it. It is my 1, it is my 2, so this is my 1 and this is my 2, is not it? Let it be my 3 and let it be my 4. So let us see 3 and 4. So coming to the proof of 3, we have mu is equal to half e to the power half plus e to the power minus half. Already you know it. So this implies what is your mu square? It is 1 by 4 this whole square, e to the power half plus e to the power minus half whole square, a plus b whole square. This is 1 by 4. It is e plus e inverse and minus 2. Now what is e plus e inverse? Again you see your delta is equal to e to the power half minus e to the power minus half. So what is your del square? It is the whole square of this e to the power half minus e to the power minus half whole square, a square plus b square minus 2ab minus 2. So what is e plus e inverse? So that means e plus e inverse is your del square plus 2. Now you substitute this over here, let it be equation star. So star follows from star. We have mu square is equal to 1 by 4. It is del square plus 4. So this is equal to 1 plus del square by 4. Okay. So is it not your 3i? So 3i is proved. So therefore your mu square is equal to 1 plus del square by 4. So this is your 3i. Now you just take the root over. So this implies what is your mu? It is root over of 1 plus del square by 4. So is it not your 4? So this is all are proved. Suppose you are asked to find the second difference of this. Okay, h is equal to 1 given. So we have del square of x square minus 5x plus 6 is equal to del of x square minus 5x plus 6. Okay, so this is equal to 1 del remain silent. Applying 1 del, x will be replaced by x plus 1, right? F of x plus 1. Okay, so as you know, del f is here f of x plus 1 minus fx, because h is here 1 here. We apply it here. So this is del of your x plus 1 square minus x square minus 5 into x plus 1 and here minus x plus, and plus del is operated upon this. It will simply 6 minus 6. It will not work. Okay. So now if you simplify it, you just simplify it, it will give you del of 2x minus 4. Now del is operated upon this. So it will be here 2 into x plus 1 minus 4 minus your 2x minus 4. Okay. And you simplify it. 4 cancelled here, and 2x also 2x is cancelled here, so it is only 2, right? Similarly, so now coming to the solution of this. Okay, del square fx is equal to del of del fx. So this will be here del of, and this will be f of x plus h minus fx, but h is here 1 here. So this is equal to del of fx plus 1 minus f of 1. Again, if del is operated, it will give you f of x plus 2 minus f of x. So this is your f of x. So if I split it out, so this is equal to del of f of x plus 1 minus del of fx, and I can write it f of x plus 2 minus f of x, and I can write it f of x plus 1 minus f of x. So if you add it, it will give you f of x plus 2 minus f of x plus 1 plus twice f of x. Just one second. So this is actually f of x plus 1. So minus twice f of x plus 1 plus fx. Okay. So now your f of x is 1 by x square plus 5x plus 6. If I factorize it, it is 1 by x plus 2 into x plus 3. Can I not find what is f of x plus 2? So this implies f of x plus 2 will be, x is replaced by x plus 2. It is 1 by x plus 4 into x plus 5. Accordingly, can I not find f of x plus 1? Can I not find f of x plus 1? And I simplified. So it will be here f of x plus 1 will be, x is replaced by x plus 1. 1 by x plus 3 into x plus 4. Now if I simplify it, so therefore my del square fx is f of x plus 2 minus twice f of x plus 1 plus f of x. If I simplify it, and it will be my. Now coming to another question, you are asked to find del to the power n ab to the power x. Okay. So coming to the solution, we have del of a b to the power x is equal to a b to the power, actually it is b to the power x, a b to the power x plus h minus a b to the power x. So this is a into b to the power x common, it is b to the power h minus 1. If I operate del of del into a b to the power x, again I will get this is your constant, it is b to the power h minus 1, it is del of ab to the power x. Now del of ab to the power x, again it will give me this, so this will give me b to the power h minus 1 into b to the power h minus 1 ab to the power x. If I go on continue, means it is b to the power h minus 1 whole square ab to the power x. It is del to the power n ab to the power x will be b to the power h minus 1 to the power n ab to the power x. Okay, this is your answer. Do more properties of del and del. I will write the properties of forward operator, and similarly backward will be the same. Now you know your del n f0 will be fn minus nc1 fn minus 1 plus nc2 fn minus 2 and plus so on minus 1 to the power n f0. If we want to prove it, you know what is your del f0? Del f0 is f1 minus f0, is not it? What is your del square f0? It is del of f1 minus del of f0 is equal to f2 minus f1 minus your f1 minus f2. So this is f2 minus 2f1 plus f2. If you substitute it, you get it. Accordingly, if I find del q f0, right, likewise it will give me f3 minus 3f2 plus 3f1 minus f0. In that way, you can continue to get your del n f0. Property number 2, del of constant into fx, okay, is constant taken out, del of fx. Then coming to property number 3, del of fx plus n minus gx will be individually del of fx plus n minus del of gx, and we similarly we can replace del by del, no issue. Then coming to the fourth property, del to the power m into del to the power n fx is del to the power m plus n fx. Okay, note that del of fx into gx is not equal to del fx into del gx. Okay, so however we see for the product what is the property, let us see. here del of fx into gx. Okay, it will be f of x plus h. It will be f of x plus h g del of gx minus gx del fx. If we want to prove it, we can prove it. If we want to prove it, we can prove it. The proof is like this: del of fx into gx will be f of x plus h g of x plus h minus fx gx. So this is equal to, you write f of x plus h g of x plus h. You have some subtract fx plus h gx and add fx plus h gx. Okay, and minus here fx into gx. Then you combine these two and this. So taking this common, it is f of x plus h, it is g of x plus h minus gx. From these two you take common gx. Okay, plus gx taken common, it will be f of x plus h minus fx. Now you see, this is nothing the forward difference here. So this is f of x plus h, it is your del gx plus gx del fx. Okay, so this is proved. So therefore here del of fx into gx is this, right? So this is proved. Accordingly, for division we have the following properties. Now coming to the division property, this is like this. It is not exactly the same as the here derivative rule, second derivative first minus first derivative second, but the denominator is something different here, and similarly here it is something different here. Okay, so just a minor difference is there, so you should remember this. The nth difference of a polynomial of nth degree is constant and all higher order differences are 0. If this is a polynomial of degree n, if I want to find what is del fx, it is f of x plus h minus fx. Similarly, if I want to find del square fx, it is del of fx plus h minus fx. And if you go on solving, we will find del n fx will be a0 n into n minus 1 into n minus 2 up to here 1 into h to the power n. So this will be a0 factorial n h to the power n. If here h is 1, if here h is equal to 1, then it will be a0 factorial n, right? In contrast, if I see d by dx of x to the power n, a0 into x to the power n, is it not here a0 into factorial n? So it resembles to the derivative for nth order difference. Okay, exactly same the nth order. But if I find n minus 1th order, it will not be like that, right? So it resembles to your derivative. Now the factorial power function. Okay, you see the nth power of a number x, we denote it x nth power like this, or this means it is the product of n factors decreased by your h. Means I can write it here x nth factorial power. Okay, we read it factorial power, or we denote it this to, right? So that means it is x minus h, x minus 2h, and we continue up to x minus n minus 1 h, right? So this is what, if my h is equal to 1, suppose my h is equal to 1, and if I ask you what is x to the power, this factorial power 2 means x into x minus 1. If I write x to the power this factorial power 3 means product of 3 factors, x minus 1, x minus 2, it, right? Means I can say here it is not usually x to the power n. X to the power n means what? X into x up to x n times, but here it is decreased by h, right? This is the difference. But the moment if your h is equal to 0, then what will happen? Here x to the power n is the same thing as here x to the power n, is not it? That means this x to the power n will be what? X minus h, x minus 2h, so on. this is x minus n minus 1 h. So this is x minus 0, x minus 0, like that, x minus 0. So it is here x to the power n. So here we can say that x to the power 0 factorial is here simply x to the power 0 is 1 here, means when this h is equal to 0, okay, then this is same only. So now it is easy to see that if I ask del x power n factorial, so this will be x plus h to the power n minus here x to the power n, okay, and in that way if we continue, it will give me nh x to the power n minus 1 factorial. So here this is factorial power function is otherwise called factorial polynomial, okay, factorial polynomial, which is increased the product of n factors. So it will behave like this, okay, as we get it this, so it will behave like this. So here it will nh x to the power n minus 1, and accordingly if I continue here del square xn, and it will be here n into n minus 1 h square x n minus 2, okay. Likewise if we continue del m xn, and it will be n minus 1 n minus 2 up to n minus m minus 1, okay, h to the power m x to the power n minus m. Here m is less than equal to n. If m is greater than m, if m is greater than n, then this must be 0, then this must be del m xn, this must be here 0, as this is what we have told here, the nth difference of a polynomial of nth degree is constant, higher order is 0, so accordingly it is like that. So as we see here, del x to the power n is here this, if here h is 1, if h is equal to 1, it is nx to the power n minus 1, is not it? So it resembles to your simple derivative formula. So we can say that here del x to the power n factorial polynomial is n x to the power n minus 1 for h is equal to 1. So is it not resemblance to d by dx of x to the power n is n into x to the power n minus 1? It is resemblance to that, okay. Accordingly if I ask 1 by del x to the power factorial polynomial, so this will be x to the power n plus 1 by n plus 1. So now is it not resemblance to integral x to the power n is x to the power n plus 1 by n plus 1, okay. So you should remember it. Now we should have some further examples. Now coming to one example, if y is equal to this, you are asked to find del y, del square y, del qy. Del qy is quite simple, it is simply only the derivative of this 3 times, it is 2 into 3 factorial is 12, but these are something different for which we need the factorial polynomial, okay. Factorial polynomial as follows. You see the polynomial here y is equal to, you can write 2 here x into x minus 1 into x minus 2, h is 1 here, okay, h is 1 here, and to make it balance we need some constant times b times for your square, we have x into x minus 1 and plus some constant c times x for this, and it is your simply your constant some d, and we adjust it accordingly, okay, to express it a factorial polynomial. So the adjustment is like this. If we put x is equal to 0, okay, then here d is equal to minus 10, because here in left hand side what is your y? This y is 2x cube minus 3x square plus 3x minus 10. So we express it in terms of a factorial polynomial. Accordingly we need to find a, b, c, d, okay. If we put x is equal to 1, then here 2 minus 3 plus 3 minus 10 is equal to here c plus d, and accordingly, so likewise putting x1, x0, x1, x2, we get the value of a, b, c, d, right. So now this polynomial is written in terms of a factorial polynomial. So therefore what is your y? y is equal to 2x, x minus 1, x minus 2. The value of b is 3. So we substitute here. It is 3x into x minus 1, and the value of c is 2. It is 2x minus 10. Okay. So now we write it. It is 2x power 3 plus 3x power 2 like this plus 2x power 1 like this. Okay, and it is here minus 10. Now coming to your del y, usual formula, derivative of x to the power n, nx to the power n minus 1 into 3, x to the power 2 plus 3 into 2, here x to the power 1 plus 2 into 1, here x to the power 0. Okay, and derivative of constant is 0. So this will be here 6x to the power 2 factorial polynomial plus here 6x to the power 1, okay, plus 2. So this is your first difference. Now if you find the del square y is del of del y, okay, so this is the derivative of this is 6 into 2x plus this is here 6 into 1 plus this is 0. So this is, I can write it 1 here. This is 12 x to the power 1 here plus 6. And similarly, if I find del qy, it is del of del square y. Okay, you see it is equal to 12 into 1 here x to the power 0. Okay, so this is 12. So as I have told you, it is here 12, right? So nth derivative here is 12 only. Okay, but n minus 1th derivative is not the same because the adjustment need the value of a, b, c, d, right? So let us now solve one more example. So now coming to another question, the first difference is given here, right? We have to obtain the function, means we have to operate 1 by del here, means it resemblance to your integral. Okay, so we write it del fx is here 9x square plus 11x plus 5. In terms of your factorial polynomial, it will be 9x square plus 11x power 1 plus 5. Okay, now I will write it. This is 9x into x minus 1. The h is being 1, h is 1. Okay, it is factorial notation plus ax, we have to adjust it, plus here b. If you put x is equal to 0, implies b is equal to 5. Put x is equal to 1, implies a is equal to 20. So here del fx will be equal to, del fx is equal to 9x, here 9, it is 9x power 2 plus 20x power 1 plus here 5. Okay, now what is fx? Fx means the integration of this, right? Fx means here 1 by del this, 1 by del this 9. So you see 9 is the constant. Integration of this is x to the power n plus 1, 3 by here 3 plus 20, it is x to the power 2 by here 2 plus 5 x to the power 1 plus integral constant, some c is there. Okay, or I write some k is there, constant of integration. So this will be in factorial notation. It is 3 here x into x minus 1 into x minus 2 plus 10 x into x minus 1 plus 5x plus constant k. If you multiply and simplify it, it is 3x cube plus x square plus x plus c, k, where k is constant of integration, okay. And we have some more examples. So you see here two missing term is there. This is a missing term, this is y0, this is y2, this is y4, and this is missing. So it is correct up to second degree. Okay, so I write it as only 3 entries, y0, y2 and y4 are given. So the function y is equal to fx can be represented by a polynomial of degree 2, right? N plus 1 means up to nth degree. So that means therefore here del qy0 is equal to 0 and del qy1 is equal to 0. So if you have your table, then the table is like this. So coming to the difference table, it is first order difference, it is second order difference, and it is third order difference. Okay, so here this is missing and this is here missing, this is here missing. So first order difference is the gap of this is y1 minus 3, this is 2 minus y1, this is y3 minus 2, and this is minus 2.4 minus y3. Then the second order difference, this minus this, is 5 minus 2y1, this minus this, it is y1 plus y3 minus 4, and it is here minus 0.4 minus 2y3. Then this minus this is here 3y1 plus y3 minus 9, and it is 3.6 minus y1 minus 3y3. Okay, now this is equal to here 0 and this is equal to 0 because it is represented by a second degree polynomial of degree 2 here, right? Second degree polynomial, because 3 nodes are given here. Okay, 3 functional values are given. So now we simplified. Del qy0 is equal to 0 and del qy1 is equal to 0. So that means 3y1 plus y3 minus 9 is equal to 0. 3.6 minus y1 minus 3y3 is equal to 0. If you solve it, you will get y1 is 2.925 and y3 is 0.225. So you get this missing value. Alternatively, we can solve it by using the shift operator. Alternatively, we can solve it like this. As you know here, del qy0 is equal to 0 and del qy1 is equal to 0. In terms of the shift operator, it is e minus 1 whole q into y0, okay, is equal to 0. So that means eq minus 3 square plus 3e minus 1 into y0 is equal to 0. And here eqy0 is here nothing but y3, right? Similarly, it is 3y1, similarly 3y2, and similarly it is 3y1, and similarly here y0. Now substitute the value of y0, y1, y2, y3, and this is equal to 0. So that means here y3 minus 3y1 and y2 value, it is y3 minus y2 value is 3, is here 2, so it is 6. y2 value is here 2, so it is 6. So it is 6 plus 3y1 minus y0 is 3 is equal to 0. So if you simplify it, it is y3 plus 3y1 minus 9 is equal to 0. This is your equation 1 as we see it here, 3y1 plus y3 minus 9, right? So this, likewise if we solve it, okay, similarly if you solve it, you will get it. Now solving this star and double star, you will solving this 2, you will get here y1 is 2.925 and y3 is 0.225. So as you know, EFX is here f of x plus h. Okay, so here e to the power 0 f of x is f of x, e to the power n fx is f of x plus nh, and e to the power minus n fx is f of x minus nh. Okay, and also you know e del is del e, right? And here e of c fx is constant taken out c fx. If e of a fx plus b gx means distributive, it is ae fx plus b gx, and e to the power m, e to the power n fx means e to the power m plus n fx. Indices property will satisfy. Note that e square fx is not e fx whole square. Okay, don't be confused. Now coming to one more important question. E is equal to e to the power hd. You know e of fx is f of x plus h. By Taylor series expansion, it is f of x plus h f dash x plus h square by factorial 2 f double dot x, and you continue like this. Okay, this is the Taylor series expansion, Taylor series expansion. So this is equal to, you can write it it is fx, you can write it h dfx, derivative of fx, plus h square by 2 factorial, second derivative of fx, and so on. So if you take common fx, it is 1 plus hd plus h square d square by factorial 2 plus so on fx, and this expansion is nothing but e to the power hd, e to the power hd fx. So therefore fx cancelled on both sides, so that means e is equal to e to the power hd. It is proved. Now with this we can have some additional question. So coming to the solution of this important question, as we see earlier, here e is equal to e to the power hd, implies here hd is equal to ln e. Also you know e is equal to here 1 plus del, already we have seen it. So now coming to the second question, so e is equal to hd is equal to ln e. What is here e here? E is 1 plus delta, it is ln 1 plus delta, right, ln 1 plus delta. Again here hd is equal to, here again here hd is equal to e, hd is equal to log e. Can you not write it? Minus 1 into log e to the power minus 1, and this e to the power minus 1 here is minus of ln 1 minus inverted delta, is not it? So e inverse is, do you not know that e inverse is here 1 minus inverted delta? So this thing we are using here. Okay, so these three things are proved. hd is log this, is log this. Now coming to the last aspect, here mu into del. Here mu into del is half e to the power half plus e to the power minus half. This is your mu, and del is e to the power half minus e to the power minus half. Now it is a plus b into a minus b. Okay, a square minus b square, it is e minus e inverse. Now the value of e you substitute, it is half e to the power hd, and it is minus e to the power minus hd. Okay, so is it not your expansion of sine? It is e to the power x plus e to the power minus x by 2 is sine hyperbolic x, is not it? So we can write it, it is your sine hd. Okay, so therefore here hd is equal to sine inverse mu delta. Okay, so now if you combine all these things, so therefore you get here hd is equal to log 1 plus del is here minus log 1 minus inverted del is sine inverse mu delta. So it is proved. Now coming to the proof of this, as we have seen, what is here efxi is here e to the power hd fxi we have seen, is not it? So this implies my e is equal to e to the power hd. Again we have seen del fxi is e minus 1 fxi. So this is equal to e to the power hd minus 1 fxi. So we have seen, so this implies here e to the power hd is equal to del plus 1. We have already seen it. So in this way, e to the power ihd, one more thing I can write it here. So likewise, if I ask you e to the power I, it will be e to the power ihd. Similarly, I can write it here, e to the power ihd is del plus 1 to the power I. Okay, so now here f of xi is equal to f of x0 plus ih. It is e to the power I fx0. So e to the power I is e to the power ihd fx0, and e to the power ihd is 1 plus del to the power I fx0. Here binomial theorem. Okay, a plus b to the power n. Okay, NCR a to the power r b to the power n minus r summation. So this is the formula for binomial expansion. So in that way I can write it, summation j is equal to 0 to I combination j del to the power I fx0. Okay, so this is proved. So coming to the summary, many important difference operators are being discussed. Okay, and there are several properties I have discussed, so you should stick to the limited property, but most importantly you have to see the relationship among the operators. Okay, more advanced things are told, so you can learn as per your choice. So now at this juncture I just appeal to all of you, if you feel this lecture is interesting and useful, please like and subscribe to this channel, which will boost my motivation to upload subsequent lecture for your benefits. So let us close this lecture. Thank you all. Have a nice day.